Good morning, dear students. Today we are going to discuss hydrogen S block and P block chemistry. So let's start from discussion of hydrogen. The hydrogen is the first element of the periodic table having the atomic number 1. Okay, so hydrogen has three isotopes that we know so far, that are protium 1H1, deuterium 1H2 and tritium 1H3. In all these isotopes you can see that the atomic number is same 1, because hydrogen has only one electron, and mass number is different. For protium mass number is 1, for deuterium mass number is 2, and for tritium mass number is 3. Okay, the most abundant form of hydrogen is protium, that means the normal hydrogen. Okay, that is the most predominant form of hydrogen. Clear? Now let's discuss the preparation of dihydrogen or preparation of hydrogen molecule. Hydrogen is mainly prepared. The most popular method of preparation of hydrogen is the laboratory method of preparation of hydrogen, where zinc metal reacts with sodium hydroxide NaOH to give you sodium zincate Na2ZnO2 and hydrogen. Okay. In this way, we can prepare the hydrogen molecule in lab. What is the commercial production of or commercial preparation of hydrogen molecule? Commercial preparation involves the reaction of hydrocarbon. I have taken methane here. Hydrocarbon CH4. Methane is a hydrocarbon which is actually reacting with steam or water vapor. In presence of nickel catalyst at the temperature 1200 Kelvin, gives you a mixture of carbon monoxide and hydrogen. Okay, this mixture of carbon monoxide and hydrogen is actually called the water gas. Okay, this mixture of carbon monoxide and hydrogen is called water gas. So question often comes in this way, that what is water gas? So you write the preparation of water gas. So what is the preparation? Preparation is when hydrocarbon is passed, or when water vapor is passed over the hydrocarbon or over coke, that means only carbon, it gives you the mixture of carbon monoxide and hydrogen. This mixture is water gas. Okay, now this water gas is also called synthesis gas, because this water gas, that means the mixture of carbon monoxide and hydrogen, can be used for the preparation of different hydrocarbons. This mixture can be used for the preparation of different hydrocarbons like methane, ethane, and so on. Okay, so all those hydrocarbons can be prepared by using this mixture. So that's why this water gas is used for the synthesis of the hydrocarbons. That's why water gas is also called synthesis gas, or in short, syn gas or syn gas. Syn for synthesis. Okay, because water gas is used for the production of different hydrocarbons. Now let's move on to our next topic. Next topic is the properties of, what are the different properties of dihydrogen or hydrogen molecule. So first of all, reaction with nitrogen and oxygen. These are the simplest reactions, where hydrogen is reacting with oxygen in presence of catalyst to give you water, and hydrogen can also react with nitrogen to give you NH3, ammonia molecule. Okay, what are the uses of hydrogen molecule or hydrogen gas? This question often comes, that write one use or two uses of hydrogen. So mainly hydrogen is used in the manufacture of organic compounds like methanol. Okay, methanol is an organic compound which is prepared by using hydrogen gas as one of the reactant, as one of the reagent. Here you can see the reaction. Carbon monoxide is reacting with hydrogen to give you methanol. So in the production of methanol, hydrogen gas is used, right? Now hydrogen gas is also used as a rocket fuel in space research. In space research we use hydrogen as a fuel, rocket fuel. Clear? Now let's come to hydrides. Hydrides is the most important topic of this hydrogen chapter. Hydrides are basically categorized into three categories: ionic hydrides or saline hydrides, covalent hydrides and interstitial hydrides. So what is ionic hydride or saline hydride? Ionic hydrides or saline hydrides are mainly the non-volatile crystalline compounds formed by alkali metals. Okay, non-volatile crystalline compounds formed by alkali metals. They are non-conductor of heat and electricity in the solid state. So hydrides compounds are mainly those compounds where hydrogen exists as H minus. Okay, not H plus. Generally, in maximum compounds we often observe hydrogen in the form of H plus. Okay, but here hydrogen is carrying negative charge, H minus. Okay, see, so in all hydrides, hydrogen carry negative charge, H minus. Okay, like lithium hydride, beryllium hydride, magnesium hydride. They are called ionic hydrides because they are ionic in nature. They all contains H minus anion, H minus anion or H minus ion in their formula, right? And second property is of this ionic hydride is they are polymeric in nature. They are polymeric in nature. They exist as a polymeric chain. Clear? Now these hydrides, the important property of these ionic hydrides are any ionic hydrides react with water to give you corresponding hydroxide and hydrogen molecule is liberated. Let me give you example like sodium hydride here, NaH, sodium hydride, Na plus H minus. Okay, so this sodium hydride is reacting with water to give you sodium hydroxide and hydrogen gas is released, right? There are some important compounds which are very useful as a reducing agent like lithium aluminum hydride, lithium borohydride. They are also prepared by using different saline hydrides or ionic hydrides. जैसे as for example, lithium hydride can react with aluminum chloride to give you lithium aluminum hydride. It's an excellent reducing agent. Similarly, lithium hydride can react with diborane, B2H6. Diborane. This compound is called diborane to give you lithium borohydride. So lithium aluminum hydride and lithium borohydride are the important reagent in chemistry. Mainly they are used as a reducing agent. Lithium aluminum hydride is an excellent reducing agent. So question comes in this way that write one preparation of what are saline hydrides or ionic hydrides, and the question can also come in this way also that what happens when lithium hydride or sodium hydride reacts with water. Okay, so hydride compounds are mainly those compounds which contain H minus anion. Okay, here sodium hydride contains Na plus H minus. So it is sodium hydride will react with water to give you sodium hydroxide and hydrogen. Clear? Now let's come to the second category of the hydride, that is covalent hydride. Covalent hydrides are those hydrides where hydrogen combines with p block elements like carbon, nitrogen, oxygen, right, to give you different compound like CH4, ammonia, water. The hydrogen reacts with carbon to give you CH4. Hydrogen reacts with nitrogen to give you ammonia, and hydrogen reacts with oxygen to give you H2O. Okay, they are all hydrides, but they are not ionic hydrides. They are covalent hydrides because in these compounds all the bonds are generally covalent bonds. Okay, they are covalent in nature. Their bonds are covalent in nature. Carbon hydrogen bonds are covalent. Here also nitrogen hydrogen bond is covalent bond. Here also hydrogen oxygen bond is covalent bond. Clear? So that's why they are covalent hydrides. Okay. The third category of hydride is interstitial hydride, or they are also called metallic hydride or non-stoichiometric hydride. So what is the definition of this kind of hydride? So they are the hydrides where the hydrogen combines with D and F block elements. Okay, hydrogen combines with D and F block elements, and here in this compound formula the hydrogen is not present as the number of hydrogen atom is not integer. They can be fraction. Okay, here in the formula also you can see lanthanum hydride. Okay, lanthanum hydride has the formula LaH2.87. That means number of hydrogen atom is not an integer like 1, 2, 3. It's a fraction, 2.87. Similarly, palladium hydride. Palladium hydride has the formula PdH0.6. So these are the hydrides where the hydrogen atom is mainly combining with D and F block elements, and number of hydrogen atom is not integer. They are present mainly in a fractional amount in the compound. So they are all interstitial hydrides or non-stoichiometric hydrides. So 3 marks question can come from the hydride concept only, that explain the different types of hydrides, write their formations, or write the associated reactions. Okay, or specific reactions of the hydride can also come in this way, right, as I said earlier. Now let's move on to the next topic, structure of H2O and ice. This is very important structure of H2O. H2O is a covalent hydride, we know. Here hydrogen oxygen bond is a covalent bond. Here also this bond is a covalent bond, and it is a bent molecule. Water is a bent molecule, as we have already learned in the VACPA theory, that water has a bent structure, and this bond angle, this is the bond angle, this bond angle is 104.5 degree in a water molecule. But in the structure of ice, you can see over here that this is a complicated structure. This is the structure of ice, where one water molecule is surrounded tetrahedrally by other 4 water molecules. One central water molecule is surrounded by 4 water molecules in a tetrahedral way, in a tetrahedral fashion. Okay, this is the first, second, and this is the third, and this is the 4th water molecule. They are connected with the central water molecule in a tetrahedral fashion, in a tetrahedral arrangement, and this is the structure of ice, and they are the hydrogen bonds. We already discussed hydrogen bond in the chemical bonding chapter. There I said that hydrogen bonding is mainly formed between the electronegative atom and the hydrogen, right? So here you can see the hydrogen bonding between oxygen and hydrogen. Oxygen is the electronegative atom carrying negative charge. Hydrogen is the electropositive atom carrying positive charge. So there is a hydrogen bonding over here. Similarly, here also hydrogen bonding is there. So many hydrogen bonding you can see in this structure, and this is the structure of ice. Okay. Now, what are the chemical properties of water? So first of all, water is an amphoteric compound. It can act as a both acid and base. Amphoteric compounds are those compounds which can act as both acid and base. So water sometimes act as acid, sometimes base. So water, when combines with ammonia, it will act as a acid. So acid, what is the function of acid? Acid release H+. So water, if releases H+, it will turn into OH- only. Okay. Similarly, so water, when combined with ammonia, it will release the H+ and converts into OH-, and that H+ will be taken by NH3, and NH3 is converted to NH4+, right? That means one H+ is transferred from water to ammonia. Water is releasing the H+, converting into OH-, NH3 is accepting H+, converting into NH4+. So water is acting as a acid. Similarly, water can also act as a base, where water combines with H2S, hydrogen sulfide. So water is acting as a base over here, where water is accepting proton from H2S and converting into H3O+, and H2S is releasing the proton, converting into HS-. Okay, water is acting as a base over here, because base always accept proton, accept H+. So base is this water is accepting H+ from H2S and converting into H3O+. Clear? Now water can also act as a redox reagent. Water can also participate into different redox reactions, like water is reacting with sodium here, converting into sodium hydroxide and hydrogen. That means water is being reduced. Water is being reduced to hydrogen. Water to hydrogen, this conversion is reduction. Na? Water to hydrogen, this conversion is reduction, because in this conversion oxygen is getting eliminated, and elimination of oxygen is called reduction, right? So who is reducing water? Sodium is reducing water. Okay, so sodium is reducing water and converting into hydrogen, right? So here water is participating in redox reaction. Okay, so we have the next topic, hard and soft water. Many questions you can expect from this. What is hard and soft water? Define hard and soft water. Explain the reason of hardness present in water, and so many associated processes to remove this water, to remove this hardness of water is also there. Okay, and from that topic also you can expect questions. So it's a very important topic, hard and soft water. So first of all, we have to know that why does the hardness appear in water, right? So the main reason, that is primary reason that is considered for the hardness of water is the ions, calcium, magnesium, they are present as a salt. Okay, what salt? Calcium hydrogen carbonate, or magnesium hydrogen carbonate, or calcium chloride, or magnesium chloride, or calcium sulfate, magnesium sulfate. These salts are present in water, and which is primarily responsible for the hardness of water. Okay, so how do we remove these salts from water so that we can make the water from hard water to soft water? Okay, so there are two types of hardness that is there. One is temporary hardness of water, and another is permanent hardness of water. Temporary hardness of water is mainly due to magnesium hydrogen carbonate salt or calcium hydrogen carbonate salt. Okay, when they are present in water, they cause the temporary hardness. Okay, so hard water, what is the problem with the hard water? Hard water is unsuitable for laundry purpose or washing purpose. Hard water is unable to remove the dirt of our clothes easily, right? So hard water, we need to remove this problem by different types of method. Okay, so temporary hardness of water is mainly removed by two processes, boiling and Clark's method. Okay, the boiling method is the most easy method of removing temporary hardness of water. So when water is boiled, suppose there is water you are boiling, and that water contains some hardness that is due to magnesium hydrogen carbonate salt or calcium hydrogen carbonate salt. So we have to remove these salts from the water so that we can convert that hard water into a soft one, right? So magnesium hydrogen carbonate, when you boil the water, this salt converts into magnesium hydroxide. Okay, when you boil water that contains this salt will be converted to magnesium hydroxide. Okay, and carbon dioxide will be liberated. Similarly, calcium hydrogen carbonate or calcium bicarbonate, when boiled, it gives us calcium carbonate, water, and carbon dioxide. So these magnesium hydroxide and calcium carbonate, these exist as precipitate. Okay, when you boil the water, these salts will be converted into the precipitate of magnesium hydroxide and calcium carbonate, right? And this precipitate can easily be removed from a solution by simply filtration process. Okay, if you filter after successful boiling, if you filter the water, these salts, these compounds, that means this precipitate will get stuck in the filter paper, and from downside we will get the soft water, right? So this is one method. Another method is Clark's method. In Clark's method, what we do, we actually add lime. Lime means calcium hydroxide. We actually add lime to hard water. Okay, so suppose there is a water containing some hardness, that means containing calcium bicarbonate salt. So this salt, water containing salt, when combines with lime, when you are adding lime, that means this lime, calcium hydroxide, will react with this calcium bicarbonate or calcium hydrogen carbonate to give you calcium carbonate precipitate. Okay, calcium hydrogen carbonate will be converted to calcium carbonate, that means calcium carbonate precipitate. Clear? So this calcium carbonate precipitate can easily be removed by simply using the filtration process. If you use filtration process, calcium carbonate precipitate will be removed. That means the hardness is removed. Clear? Now, so these are the process where so now we shall discuss the processes to remove the permanent hardness of water. So mainly permanent hardness of water appears due to the chloride and sulfates salts of calcium and magnesium. So calcium chloride, magnesium chloride, calcium sulfate, magnesium sulfate. These are the salts responsible for the permanent hardness of water. Okay, permanent hardness of water is removed by the following process. Number one is Kalgan's method. Kalgan's method is one of the way to remove the permanent hardness of water, where we use sodium hexametaphosphate. These are the formula. This is the formula Na6P6O18. Sodium hexametaphosphate that has the chemical name Calgon, which is used, which is actually added to hard water to remove the hardness permanently. To remove the hardness. Okay. Calgan's method. So, question often asked in this way that what are the methods followed for the removing of the permanent hardness of water. So, one of the method is Calgan's method, but most important method is ion exchange method. In ion exchange method, what do we use? Sodium aluminum silicate, that is popularly known as zeolite. This sodium aluminum silicate, when it exchange its ion with the ions present in the hard water like calcium and magnesium, the hardness, the permanent hardness of water is removed. Sodium aluminum silicate has the formula NaAlSiO4. Okay, SiO4 is silicate part, sodium aluminum silicate. Okay, so when we are allowing this reagent to react with the calcium ion present in the hard water, there is a exchange of ion takes place. Sodium plus ion is there, here calcium 2 plus ion is there, so they will exchange their position among themselves. They will exchange their exchange one another. That means it will form calcium aluminum silicate, and sodium plus is removed. That means the calcium ion will exchange the sodium and forms calcium aluminum silicate, and sodium plus is removed from the substance. So in this way, this process is called ion exchange method, ion exchange process, where the two ions are exchanging among themselves and the permanent hardness of water is removed. Okay, so another important compound next that we have is hydrogen peroxide. Hydrogen peroxide is an important compound of hydrogen, where it is mainly prepared by the oxidation of 2-ethyl anthraquinol. 2-ethyl anthraquinol is an organic compound which is oxidized in presence of oxygen to give you H2O2 and other oxidized product. So this is the preparation of hydrogen peroxide compound, H2O2. So hydrogen peroxide has a ability to act as a oxidizing as well as a reducing agent. Oxidizing agent and reducing agent both. Okay, H2O2 is both oxidizing and reducing at the same time. Oxidizing agent, as an oxidizing agent of H2O2 react with PBS to give you PbSO4 and water. H2O2 here is acting as a oxidizing agent. So oxidizing agent is that substance which oxidize other substance and reduce itself. Okay, oxidizing agent is that substance which oxidize other substance and reduce itself. So H2O2 here acting as a oxidizing agent, which is oxidizing PBS to PbSO4, and itself it is getting reduced to H2O. Okay, so H2O2 here acting as a oxidizing agent, which is oxidizing PBS to PbSO4. So obviously PBS to PbSO4 is the oxidation process. Addition of oxygen is taking place, so it is obviously an oxidation process. H2O2 is oxidizing PBS to PbSO4, and H2O2 itself is reducing to water. Okay, it is reduction process. H2O2 to water reduction process. Clear? So this is the example where H2O2 is acting as an oxidizing agent. Next that we have is reducing agent. H2O2 can also act as a reducing agent, where you can see a reaction over here where iodine is reacting with H2O2, and iodine is actually H2O2 is reducing iodine to form I minus, and H2O2 is itself oxidizing to oxidized to H2O. Oxygen. Clear? So H2O2 here is acting as a reducing agent. So reducing agent is that substance which reduce other substance and oxidize itself. So H2O2 here acting as a reducing agent, which is reducing the iodine to form I minus or to form HI. H22 itself is oxidized to oxygen. H22 to oxygen is oxidation process. Removal of hydrogen is oxidation, right? So H22 is itself oxidized to oxygen and it is reducing iodine to I minus. Okay, so H22 here acting as a reducing agent. Now next compound, important compound that we have that has a large application in industrial world, that is heavy water or D2O. Okay, so we know deuterium is the another isotope of hydrogen. Okay, it is mainly deuterium water, that means the D2O, heavy water, is mainly prepared by exhaustive electrolysis of water. If you put water in a beaker and put some cathode and anode and pass electricity through it, through water, that is called electrolysis process. Electricity, we have to supply electricity by using some battery, obviously. So if we use if we pass high amount of current or high amount of electricity through water for a long period of time, it's called exhaustive electrolysis. Okay, so if you do such kind of electrolysis of water, we will get D2O as a product. So what are the uses of D2O? D2O is mainly used in nuclear reactor, and where D2O acts as a moderator. Moderator, what is the function of moderator? Moderator actually slow down the speed of neutrons that come up in different radioactive processes, right? Now, second use of D2O is it is also used in the preparation of other deutero compound like CaC2. When reacts with D2O, it gives C2D2. These C2 and D2, they will combine to give C2D2, and calcium will combine with oxygen to give calcium OD2. Okay, so this C2D2 preparation is only possible by using D2O, right, with CaC2. Calcium carbide. CaC2 is calcium carbide. Calcium carbide when reacts with heavy water to give deutero compound like C2D2. So such kind of deutero compounds are mainly formed by using D2O, and that is the another use of D2O. So question comes in this way: write the preparation of D2O or heavy water and write two uses of it. So these are the two uses of D2O. Now we have come to the discussion of S block elements. So S block elements are mainly group 1 and group 2 elements present in the periodic table. Okay, group 1 elements have the electron configuration ns1, and group 2 elements have the electron configuration ns2. Clear? Group 1 elements like lithium, sodium, potassium, rubidium, they are group 1 elements. Group 2 elements are like beryllium, magnesium, calcium, strontium, they are group 2 elements, right? So these are group 1 and group 2 elements that we shall discuss over here in this S block element discussion in a detailed way. Okay, so let's come to the points, come to the topics one by one. So first of all, ionization enthalpy of these elements. Group 1 elements are called alkali metals. Group 2 elements are called alkaline earth metals. Okay, group 1 elements and group 2 elements are mainly metals like lithium, sodium, calcium, magnesium. They are all mainly metals, and metal have a high tendency to release the electron, right? So all these group 1 and group 2 elements have the high tendency to release electrons. That's why they are metals, right? So they can easily release the electrons from their atoms, right? Now, since they can easily release electrons, their ionization enthalpy is very, very less. Okay, ionization enthalpy value is very, very less, because we know ionization enthalpy is the energy required to remove one electron from the atom, right? Since group 1 and group 2 elements can easily release electrons, so we don't need to put a large amount of energy. Rather, we have to put a very small amount of energy to remove electron from these atoms. Okay, so that means ionization enthalpy is very, very less or very, very low for these elements, right? Now, what is the hydration enthalpy? This is a very important concept of the alkaline earth metals. That what is the trend of hydration enthalpy of alkali and alkaline earth metal. So first of all, we have to know what is hydration enthalpy. So hydration enthalpy is actually the process where the cations and anions are hydrolyzed by water. Hydrolyzed means water molecules will be accommodated surrounding the cation and surrounding the anion. Any cation or anions are generally stabilized in water. Water acts as a solvent. The cations and anions get stabilized in water. How? What is the process? Because water, we know water is a polar covalent compound. Polar covalent compound. It's a covalent compound, but the bonds are not perfectly covalent. What is the polarity of these bonds? Oxygen is negatively charged and hydrogen is positively charged. Here also oxygen negative, in this bond oxygen negative, hydrogen positive. So these are the polarity of these water molecule. So obviously any cation like sodium plus will be stabilized by the oxygen end of water, and any anion like Cl minus will be stabilized by the hydrogen end of water. Sorry. One second, just we are discussing the hydration enthalpy. So okay, so here we are. So here you can see any cation like sodium will be stabilized by the oxygen end, because sodium carry positive charge and oxygen is the negative end, so they will be stabilized each other, right? Similarly, hydrogen end will stabilize the Cl minus or anion, right? Now when sodium plus or Cl minus, they are taken in water, so many water molecules will be surrounding the cation and the anion. Okay, sodium plus will be surrounded near by the oxygen end, where Cl minus will be surrounded by water molecules, where hydrogen is near to the Cl minus. Here oxygen end is near to the sodium plus, right? Clear? Now in this process of stability, vast amount of energy is released. A high amount of energy is released, because it's a neutralization process of plus and minus, na? That means the entire system will be stable, and stable means energy will be released, right? So energy will be released. This energy that is being released is called hydration enthalpy. Now the interesting thing is, when we move from lithium to cesium, lithium plus to cesium plus, we shall see that enthalpy of hydration is becoming less. Highest energy is released for lithium, 519 amount of energy, and for cesium lowest amount of energy is released, 264. Okay, why it is like that? Because lithium plus is the smallest atom, right? Smallest in among these, right? So since lithium plus has the smallest is the smallest atom, plus one charge has the highest density over here. Everyone has the plus one charge, right? But the charge density, the density of this plus one charge is highest or maximum in lithium, because the lithium size or radius of lithium is very, very small. So in the small area, plus one charge is concentrated. So charge density is very, very high over here. So since charge density is very high, large number of water molecules will be surrounding the lithium plus. Okay, and since large number of water molecules will be surrounding the lithium plus ion, vast amount of energy or large amount of energy will be released, right? So what did we learn over here? That smaller the atom, higher is the charge density, and higher the charge density, higher is the number of water molecules surrounding this cation, and higher will be the energy released. That means higher will be the hydration enthalpy, right? Now since lithium plus has the smallest size, so lithium plus will show the highest charge density, and so many water molecules will be surrounding surrounding around it, and a large amount of energy is released for lithium, and this is the hydration enthalpy trend. Lithium plus has the highest hydration enthalpy, then sodium, then potassium, then rubidium, and then cesium. So here you can see the hydration enthalpy order: lithium plus hydration enthalpy maximum, then sodium, then potassium, then rubidium, then cesium. So as for group 2, same pattern is going to be observed. Okay, group 2 beryllium is the first member, so beryllium 2 plus will have the highest hydration enthalpy, then magnesium, then calcium, then strontium, then barium. Okay, so this is very important. Often the question comes in this way that what is hydration enthalpy? Give the trend in hydration enthalpy of group 1 or group 2 metals. Okay, so let's move on to the next topic. Okay, so reactivity towards air. Okay, how do they react with air or with atmosphere or with oxygen? Okay, here you can see that lithium reacts with oxygen to give lithium monoxide Li2O. Sodium reacts with oxygen to give Na2O2, sodium peroxide. So here is the difference. Okay, lithium reacting with oxygen to give lithium monoxide, whereas sodium is reacting with oxygen to give sodium peroxide. So here lithium differ from sodium or from other alkali metal as well in the reaction of oxygen. Okay, so always remember this: lithium oxygen combination lithium monoxide, sodium oxygen combination sodium peroxide. Okay, and other alkali metals also react with oxygen to give you superoxide compound of the elements. Clear? So lithium behaves completely differently in the respect of reaction with oxygen. Now the most important property of this alkali and alkaline earth metals is the reducing property. They are all reducing in nature. They can reduce other elements. Lithium, sodium, calcium, magnesium, potassium all can reduce other elements, because reduction means reduction has another definition. So even in the redox chapter we shall get to know all these things. Redox reduction process means the ability to give the electron to others, right? So if any element has the ability to give electron to others, that element is supposed to be reducing in nature, right? So we already know that group 1 and group 2 are the elements which have the high tendency to release or to liberate the electron. So they can all these elements of group 1 and group 2 can give their electrons to others, can release the electrons to other elements, right? So they can reduce the other elements in this way. So that's why group 1 and group 2 elements are strongly reducing in nature. They are strongly reducing in nature. Now what is the reactivity towards halogen? Okay, alkali and alkali metals like sodium, potassium, magnesium, calcium, all these alkali and alkaline earth metal reacts with halogen like fluorine, chlorine, bromine, iodine in the following way to form the halide compound. Okay, so sodium reacts with halogen chlorine to give you sodium chloride. Potassium reacts with halogen chlorine to give you potassium chloride. Magnesium gives magnesium chloride, and calcium gives calcium chloride, CaCl2. Okay, now let's move on to the next topic: oxides of group 1 and group 2. Oxide means the group 1 and group 2 the combination product with oxygen, right? So group 1 and group 2 elements form oxides of the type MO, MO2, M2O, M2O2. जैसे as for example, magnesium reacts with oxygen to give you MgO, that has the type MO type. Sodium reacts with oxygen to give you the oxide sodium oxide Na2O, that has the type M2O. Potassium has the type K2O, M2O type, K2O, potassium oxide. Sodium reacts with oxygen to give you sodium oxide Na2O2, and that has the type M2O2. Okay, now the next topic that we have is the solution in liquid ammonia. Many questions you can expect from this topic, because this is one of the most important topics, and the question comes often in this way: why do the alkali and alkaline earth metals show deep blue color in the liquid ammonia solution, right? So the answer is, when any group 1 or group 2 elements you dissolve in water, suppose you are dissolving any group 1 or group 2 element in ammonia, what will happen? This element, group 1 or group 2 element, they will release the electron and converts into M+. M is the group 1 or group 2 element. Okay, suppose M is the group 1 or group 2 element, so M will release the electron to give you M+, just like sodium plus, potassium plus, just like that. And the electron will also react with ammonia to give you this type of substance, this type of chemical species, that is called ammoniated electron. Okay, so it is the ammoniated cation. Ammoniated means the cation and the anion. What is the cation? M plus. And what is the anion? Electron. Electron is the anion, right? E minus. Electron carry negative charge, right? So after the release of the electron, the M plus will be surrounded by ammonia molecules, just as we saw in case of the hydration enthalpy. Water molecules surround the cation. Similarly here ammonia molecules are surrounding the cation M plus, and giving you ammoniated cation. Similarly electron will also be surrounded by ammonia molecules to give you ammoniated electron. And this ammoniated electron is actually responsible for giving the, or for imparting the blue color in solution. Okay, as we discussed in structure of atom chapter also, that electron is mainly responsible for the origin of color in a compound, right? Electronic transition from one energy state to the another energy state. This electronic transition that takes place in atom is actually responsible for color of every compound, right? So this is the topic where the question comes in this way, that why do all the alkali and alkaline earth metals show deep blue color? So what is the reason? The reason is that after the loss of the electron, it forms ammoniated cation and ammoniated electron, and this ammoniated electron is actually responsible for the deep blue color in solution. Now let's elaborate this point more clearly so that you can understand it very clearly. Here you can see I have taken the example of element sodium, which is in presence of ammonia solvent. It is releasing one electron and converting into Na plus and the electron E minus. Na plus will be surrounded by ammonia molecule. Similarly E minus will also be surrounded by ammonia molecules. Okay, this is called ammoniated sodium plus, and this is called ammoniated electron. And this ammoniated electron is actually producing the color of the solution of sodium in ammonia, right? Solution of sodium and ammonia has the deep blue color, and this deep blue color is for the electron, because electron, always we know electron moves from lower energy to the higher energy after absorbing certain amount of energy, right, from the environment, right? So this electron will also go to the higher energy state. So when after going to the higher energy state, the electron will be unstable, so the electron will be returning to the lower energy state again, right? And during returning of the electron from higher to lower energy state, some amount of energy will be released, right? Some amount of energy will be released, and this energy that is being released by the electron while returning from the higher to the lower orbit, the energy comes out in the form of light, and that light is actually the blue light that actually strikes our eyes, and we see the solution of sodium in liquid ammonia as a deep blue solution. Okay, so this is the detailed explanation of the origin of the deep blue color of any alkali or alkaline earth metals in liquid ammonia solvent. Okay, now one second. So here another most important topic is anomalous property of lithium, and why does lithium behave abnormally with respect to the other elements of group 1, and what is the difference between lithium and other alkali metals. That means the same topic, why does lithium behave abnormally with respect to the other elements of group 1. So what are the differences, what are the reasons for lithium to be different or to show different properties? So the main reasons are, we have already discussed these reasons in chemical bonding also. So these reasons are, lithium has the smallest size, highest charge by radius ratio, and highest electronegativity. So these are the reasons, probable reasons for which lithium behaves abnormally with respect to the other elements of group 1. Okay. The second reason is, lithium is least reactive. What is the difference between lithium and other elements? Lithium is least reactive and strongest reducing agent among the alkali metals. Among all the alkali metals, lithium is least reactive and strongest reducing agent. Right. Number 2 point is, unlike the other alkali metals, it forms monoxide. We have already seen this reaction, oxide reaction of elements, reaction of group 1 and group 2 elements with oxygen. Lithium forms lithium monoxide, while other elements forms peroxide or superoxide compound, as we saw just now. Right. Lithium forms lithium monoxide. Other elements like sodium forms sodium peroxide. Okay, so this is the difference between lithium and other alkali metal. Lithium reacts with nitrogen to give you lithium nitride, while other elements react differently with nitrogen. So these are the points where lithium differ from the other alkali metals. Another point of difference is that lithium nitrate, if you heat, you will get lithium monoxide and NO2 and oxygen. While sodium nitrate, if you heat, you will get sodium nitrite, NaNO2 and oxygen. So the reaction of lithium nitrate and sodium nitrate are totally different. So in this respect also lithium differs from the other alkali metals, like lithium differs from sodium. Right. Now next point is, lithium fluoride and lithium monoxide are less soluble compared to the fluorides and oxides of other alkali metals. So main reasons that is actually making lithium different from the other alkali metal are: lithium has the smallest size, highest electronegativity, highest charge by radius ratio, and specifically these are the points where lithium differ from the other alkali metals. Okay. Now what are the similarity between lithium and magnesium? We know the diagonal relationship concept as discussed in the chemical bonding chapter, that diagonal elements like lithium and magnesium show some similarity, right, in chemical properties as well as in some physical characteristics, and that's why it is called diagonal relationship between lithium and magnesium. So what are the similarities between these two elements? Both lithium and magnesium are harder and lighter. Both lithium and magnesium forms nitrides of the type Li3N and magnesium Mg3N2. Okay, by the direct combination with nitrogen. And the third point is, the carbonates of both lithium and magnesium on decomposition gives metal oxide and carbon dioxide. Lithium carbonate, if you heat, you will get lithium monoxide and carbon dioxide. Similarly, magnesium carbonate, if you heat, you will get magnesium oxide and carbon dioxide. Right. So these are the similarity that these two elements exhibit in chemical properties. That's why lithium and magnesium are said to show or exhibit the diagonal relationship. So question comes in this way, that what is diagonal relationship? Write two similarities of lithium and magnesium. Okay. So these are the similarities. Okay, between lithium and magnesium. Now, as lithium differs from the other alkali metal, beryllium also differs from the other alkaline earth metals. Okay, beryllium is a member of group 2 and it is the first member of group 2. So beryllium differs from the other alkaline earth metals. Sorry. Okay, because of the same reason. Beryllium has the smallest size, highest ionization enthalpy, highest charge by radius ratio. So these are the reasons why beryllium differ from the other alkaline earth metals. Okay. Specifically, the point of differences are like beryllium contains 2s and 2p orbitals, whereas other elements can expand their octet. Okay, because other elements have available d orbital for expanding their octet and they can form more than 4 bonds, but beryllium can form maximum 4 bonds, because 2s has 1 orbital and 2p has 3 orbitals, so total 4 bonds are possible surrounding beryllium, right? Whereas other elements of group 2 forms more than 4 bonds because they have available d orbital in the valence shell, right? So this is one point of difference. Another point of difference is that unlike oxides and hydroxides of other members, beryllium hydroxides are amphoteric in nature. Beryllium hydroxides are amphoteric in nature. So this is another point of difference from beryllium to the other alkali metal. So unlike oxides and hydroxides of other alkali members, beryllium hydroxides are amphoteric in nature. Okay. So other group 2 hydroxides are not amphoteric. Only the beryllium hydroxide is amphoteric in nature. So this is the point of difference of beryllium from the other alkaline earth metals, right? Now, like lithium magnesium comparison, that is the diagonal relationship, beryllium is also in diagonal relationship with aluminium. So what are the similarities between them? Number one point is both beryllium and aluminium are not attacked by acid, because when beryllium and aluminium are exposed in air, beryllium reacts with oxygen of atmosphere to give beryllium oxide. Similarly, aluminium reacts with oxygen of atmosphere to give aluminium oxide. And this beryllium oxide and aluminium oxides are actually they act as a protective oxide layer and do not let these elements to be attacked by acid or other substances or other reagents. Okay, so beryllium and aluminium both are not attacked by any kind of acid or any kind of other substance because they have the protective oxide layer. Beryllium oxide layer is surrounding beryllium, aluminium oxide layer is surrounding aluminium. Second point of similarity is beryllium gives berylate after reaction with NaOH. Berylate has the formula BeOH whole 4 2 minus. Similarly, aluminium gives aluminate after reaction with NaOH to give aluminate. Aluminate has the formula AlOH whole 4 minus. So these are similar kind of reactions beryllium and aluminium exhibit. Now the third point of similarity is both beryllium and aluminium hydroxides and oxides are amphoteric in nature. This is a very important point. Aluminium oxide, beryllium oxide, aluminium hydroxide, beryllium hydroxide, all are amphoteric in nature. So this is also one of the similarity between them. So these are few topics, most important topics that can come in your exam of class 11 from hydrogen and S block. So hope you all have understood all these topics. Thank you.